everyone. I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. So in our last video, we have discussed about waves, certain parameters related to waves like phase of a wave. So what is the phase of a wave? Where we consider state of a particles in a medium with respect to their position and direction of motion. And if we consider two waves, two light waves, how we can measure phase difference between those two waves. So we have seen that in order to measure phase difference, we have to consider either in terms of time interval or it has to be in terms of angle. So we can measure with respect to angle or it can be with respect to time. And there we have discussed about in-phase waves as well as out-of-phase waves. So if their positions are exactly matching, then we say that they are in-phase waves. Whereas if their positions, if they are out of phase, like their positions, crest of one wave falls on trough of another wave, then in that case we'll say that they are out of phase. So we have discussed about coherent waves also. So what are coherent waves? Suppose if we take two waves, if they maintain zero or constant phase difference, then we call those waves to be coherent waves. And then we have discussed about finding path difference between the two waves. And generally how we'll find path difference between two waves? If we take two waves that are coming from two different sources, but they are reaching a single point on the screen. So when we are trying to find path difference, what we have to do, we have to take difference in the distance traveled from two different sources reaching the same point. And we know that whenever we are trying to find path difference, we have to draw a perpendicular, and that perpendicular, it will help us to find path difference. And also we have taken a very important relation between phase difference and path difference. Suppose if you call our phase difference to be delta, then that phase difference, it is given as 2 pi by lambda times the path difference. Okay, so it is given by 2 pi by lambda times the path difference. So this is our phase difference, and whereas this is our path difference. And also in our last video, we have discussed about experimental setup used by Young's in order to observe the phenomena of interference. And that particular experiment, it is called as Young's double slit experiment. And what is this experimental setup? Here what we have done, usually we'll take a source S. We can see in this figure, we have taken one pinhole. Also, we can take one single slit. And this particular pinhole or single slit, it has to be illuminated by either sunlight, or to be more convenient sake, we can make use of even monochromatic light. We can also make use of monochromatic light. So we know difference between monochromatic light and sunlight, whereas our sunlight, it consists of different colors of different wavelengths. Whereas if you take monochromatic source, there it will have single wavelength lambda. So we can use either sunlight or we can use even monochromatic light, and that light, it is made to fall on a single slit, and once your light goes through this pinhole, then we'll have spherical waves coming out of this pinhole. And when we take that spherical wavefront, we are explaining its crust and trough by using two different colors. Suppose if we take red to be crust, then yellow to be trough. Of course, that spherical wave which is passing through this slit, again it is made to pass through two slits which are kept on a screen, and these two slits, they are very close to each other. And what is the distance of separation between these two slits? It is taken as small d. What is small d? Small d represents distance between the two slits, and this d value, it will be very, very small. And then what you will observe here is, once that spherical wavefront coming from this single slit passes through these two more slits, then your spherical wavefront, it gets divided into two parts. And here what you will observe here is, now superposition of these two spherical wavefronts takes place, and as a result of this we'll get interference pattern. And here why Young's he has used two slits? Because as I told you in my previous session, that if you consider waves coming from two different sources, they can never be in phase with each other. They will not give rise to interference pattern. So in order to get interference pattern, these waves, they should be in phase with each other. So that's why what he has done, he has used a single source and he has divided light into two parts by making them go through two different slits or two different pinholes. And here, if you consider spherical waves coming from these two different sources, what you will observe here is we are considering the points. If we consider the points where crust of one wave falls on crust, that is when yellow coincides with yellow and red coincides with red. So if you consider these points, when crust due to one wave falls on the crust due to another wave, then trough of one wave on trough of another wave, then what happens to resultant intensity? Resultant intensity will get added up, which will give rise to maximum intensity, and here we'll have central bright fringe. Whereas at points, if you see these points where yellow is falling on red, it means that when crust due to one wave falls on trough due to another wave, then what happens to resultant intensity? It will be difference of intensities due to individual waves, and we'll have minimum intensity, which is nothing but the dark fringe. And here one more thing in this experimental setup, what we have to understand here is the small d, it is the distance between those two slits, whereas what is capital D? Capital D is distance of the screen from those two virtual coherent sources. Now these two slits, they'll act as two virtual coherent sources. So distance of these two virtual coherent sources from the screen, it is taken as capital D. And what we have to understand here is D is very, very small. This, what is the D distance between two virtual coherent sources? We have to maintain it to be very, very small. Whereas distance of these two virtual coherent sources from the screen, it should be very, very large. Then only we'll have very good interference pattern forming on the screen. And what is our interference pattern? Having alternate bright and dark fringes. So this is about the experimental setup used by Young's in order to get interference pattern. And very important thing. So what are the conditions in order to get interference? There are in order to get good interference pattern, we have to follow certain rules, and those rules, they are given here, they are listed here. First thing is those two light sources, they should be coherent. So we have to make use of two coherent sources. So in order to have two coherent waves, we have to create two coherent sources. So for that, what we are doing, light from the same source, it is made to pass through two virtual sources. So first thing is light waves, they should be coherent, and whatever two sources we are taking, so they should be able to emit light waves of same wavelengths and frequency. And when it is possible, when you make light from the single source pass through those two sources. So what are the things which we have to take? First thing, very important thing we have to consider is whatever waves are coming, they should maintain phase. And second thing is both those interfering waves, they should be of same wavelength and frequency. And separation between the two sources. Here we are talking about small d. What is small d? Small d is distance between those two virtual coherent sources. The d, it should be very, very small. And whereas distance between the two sources and the screen should be large. And here we are talking about capital D. So as we have seen in our previous figure, what is capital D? Capital D is distance of the screen from those two virtual coherent sources, and we have to maintain this D to be very large. Whereas distance between those two virtual coherent sources, which is represented by small d, it should be very, very small. And then next is when we are taking interference fringes on a screen, when we are recording fringes on a screen, we have to maintain that background of the screen, it should be dark. Then we should be able to see beautiful pattern of bright fringes on the screen. And apart from their wavelengths and frequency being same, the amplitudes of light waves should also be equal to, they should also be nearly equal to each other. And one more thing what we have to understand here is diameter of those coherent sources which we are using. The diameter, it should be very, very small. The sources should be very, very narrow. Suppose if you are making use of pinholes or single slit, their width we have to maintain it to be very, very small. And it is better interference pattern will be obtained when we make use of monochromatic source of light, where you are maintaining single wavelength of light. So if we take care of all these points, then we are going to get good interference pattern on the screen. And what are those important points we have to take into consideration? First thing is two light waves that are undergoing superimposition. In order to get interference pattern, they should maintain phase or they should be coherent with each other. they should have both those two waves, they should have same wavelength, same frequency, and apart from that, it is good to have their amplitude also nearly equal. And then we are saying that it is better if we make use of a monochromatic source of light having single wavelength. And then distance between those two coherent sources, it should be very, very small, and width of each coherent source, we have to make it to be very, very small. It means that our sources, they should be narrow, and distance of these two virtual coherent sources from the screen, which is represented by capital D, it should be very, very large. So we have to take care of all these things in order to get good interference pattern. Then to proceed further, now next topic of discussion is analytical treatment of interference. So here we are saying that because of interference on the screen, we are able to create bright and dark fringes. Okay, so now we should try to get conditions. So what are the conditions to get bright fringe on the screen? Because of overlapping of the two waves coming from two different sources, coherent sources. And what should be the condition in order to get dark fringe on the screen because of overlapping of those two waves coming from two coherent sources? So here in this analytical treatment, we'll try to get condition for maximum intensity, which is nothing but condition for constructive interference, and then condition for minimum intensity, that is nothing but condition for destructive interference. So for that, again, I am making use of Young's double slit experiment. If we see this figure, here we have S1 and S2. What are our S1 and S2? Here S1 and S2, both of them are virtual coherent sources. So we'll call them as virtual coherent sources. Why virtual coherent sources? Because they are not actual sources of light. Light from a single source or monochromatic source, it is made to pass through two pinholes. Now these two pinholes, they will act as virtual coherent sources. Now I have taken two virtual coherent sources. Those are S1 and S2. Now as you can see, there is one wave starting from source S1 and it is reaching point P on the screen. Similarly, I have one more wave starting from source S2, from the middle point of source S2, and it is reaching point P, same point P on the screen. So what we are doing, we are taking two different waves coming from these two different coherent sources S1 and S2, and these two waves, they are starting from the midpoint of their respective sources, but they are reaching same point on the screen. Now, next and one more thing what we have to consider here is, we are considering that these two waves, they are having same amplitude A. And what is the phase difference between these two waves? That phase difference we are giving by delta. So this is the phase difference between these two waves. Now, what you will observe here is, now we have to get conditions in order for the point P to be bright and for point P to be dark. So for that, what I am doing here is, first I will try to define their displacements. And what I am saying here is, this wave which is coming from the source S1, its displacement I am defining it as Y1. And how I am giving it? I am taking it as A sine omega t. So I am defining it as A sine omega t. What is Y1? Y1 is displacement of wave that is coming from the source S1, and A is the amplitude of that wave. And in this case, what is omega? Of course, omega is angular frequency and t is time. Okay. Similarly, displacement of the wave that is coming from the source S2, it is given by Y2. And how it is given? Y2, it is given as A sine omega t plus delta. So why I have taken plus delta? Because here we are saying that both these waves, they are maintaining some constant phase difference. And what is the phase difference? Phase difference is delta. Now, what you will observe here is, because of superposition of these individual displacements Y1 and Y2, we'll try to consider what will be the resultant displacement Y at the point P on the screen. So for that, as I have told you, first displacement it is given by A sin omega t. Second displacement it is given by A sin omega t plus delta, where delta is the phase difference between these two waves. Now if these two waves undergo superposition, then according to principle of superposition of waves, here we are making use of principle of superposition of waves. How is our resultant displacement given? Resultant displacement it is given as sum of displacements due to individual waves. And what is the displacement due to first wave, that is wave that is coming from the source S1, it is given as A sin omega t, whereas displacement that is coming from the second source, it is A sin omega t plus delta. Now if we try to simplify here, what we are doing here is we are expanding sin omega t plus delta. Here it is in the form of sin A plus B, trigonometric relation. And according to this, sin A plus B, it is written as sin A cos B plus cos A sin B. So if I try to expand it in a similar way, sin omega t plus del, it can be written as sin omega t cos del plus cos omega t sin del. Then after that, I try to take out common term A sin omega t. Then I end up having A sin omega t into 1 plus cos del plus A cos omega t sin del. Now here I am introducing two factors. Those two factors I am calling it as r cos theta and r sin theta. And how I am defining this r cos theta and r sin theta? R cos theta, it is given as A into, so this particular term, this A 1 plus cos del, I am taking it as r cos theta, whereas A sin del, I am taking it as r sin theta. If I substitute these two parameters, r cos theta and r sin theta, in my resultant displacement equation, then I end up having like this. Now again, it is in the form of sin A cos B plus cos A sin B. So if I try to simplify it, my resultant displacement, it comes in this particular formula, which is given as r sin omega t plus theta. What is r? R is the resultant amplitude. So here r is resultant amplitude and our y is a resultant displacement because of superposition of two waves whose displacement is given by y1 and y2, and both of them, they are coming from two coherent sources, but they are reaching same point on the screen. Okay, and that resultant displacement, its phase, it is given in terms of theta. And as you have seen that those two waves which we have taken, individual waves y1 and y2, they are having same angular frequency. Omega also we have taken their same amplitude. So we end up having a resultant displacement like this. And then now we try to see what is the resultant intensity because of superposition of these two waves whose displacements they are given by y1 and y2. For that, I am making use of expressions for r cos theta and r sin theta. R cos theta, as we have seen here, it is given as A into 1 plus cos del, and r sin theta, it is given by A sin del. Now what I am going to do, I am going to first square these two equations, squaring and then adding. So if I do it here, I end up having r square, because here on the left hand side, this will become r square cos square theta, this will become r square sin square theta, and if we add, we'll have r square into cos square theta plus sin square theta, and we know that cos square theta plus sin square theta is 1. So left hand side, we end up having r square. Then on right hand side, we have a square into 1 plus cos del whole square plus a sin del whole square. And if we simplify this, we end up having it as square of resultant amplitude is 2a square. What is A? A is amplitude of individual wave, whereas capital A, R is amplitude of our resultant wave or resultant displacement, which is caused because of superposition of waves, into 1 plus cos del. Now here, if I try to simplify this expression further, then 1 plus cos del, I can write it as 2 cos square delta by 2. So finally, how we can write for intensity? Our expression for intensity is nothing but square of amplitude. And what is the formula we got for square of amplitude? 4a square cos square del by 2. This is very important relation. So what is this I? I is intensity At the point P, if we go back to our experimental setup, so this is our point P, and at the point P, what is the expression for intensity we got because of superposition of these two waves? It is given as 4a square cos square del by 2, where a is the amplitude due to individual wave, and here we are maintaining that these two waves, they are having same amplitude a, and delta, it is the phase difference between those two waves. Now next we will see from this intensity expression what are the conditions we are going to get. So here I have taken two cases. First case is getting condition for constructive interference, and second case is getting condition for destructive interference. Now as we know that when we'll have constructive interference, so as we know that when waves are in phase with each other. So what do you mean by in phase with each other? Where they maintain zero phase difference, when their positions are exactly matching. And we know that because of constructive interference, their amplitude get added up, so the resultant intensity will be maximum intensity. And if we see this expression, we know that we got for intensity I as 4a square cos square del by 2, and what is the maximum value we can have for cos square del by 2? We know that maximum value is 1. So cos, it can have its maximum value to be 1. So here I have to take my cos square del by 2 to be 1 in order to maintain point P to be maximum. Intensity at point P to be maximum, I have to consider in this formula for resultant intensity. Here cos square del by 2, if I take it as 1, and for which values of del, your cos square delta by 2, it will be 1. For delta, it is equal to 2n pi, and our n, it is an integer. And what are the values taken by this integer? It is 0, 1, 2, 3 and so on. So what are those values of phase difference? So if I substitute n is equal to 0, then it will be 0. If I substitute n is equal to 1, then I will have 2 pi and 3 pi. So 2 pi and then 4 pi and then 6 pi. So these are the multiples of pi, which will give rise to maximum intensity. And I think once we know the phase difference, we can find path difference. What is the relation between phase difference and path difference? We know that phase difference is 2 pi by lambda times the path difference. So from this, what is our path difference? Lambda by 2 pi into phase difference. If I make use of this formula, so what should be the path difference between those two waves coming from two different sources in order to make point P on the screen bright? That path difference, it is integral multiple of lambda. So what do you mean by integral multiple of lambda? It will take 0, then lambda, then 2 lambda, 3 lambda and so on. So these are the values of path difference, and these are the values of phase difference for the point P on the screen to be bright. And what is the value of maximum intensity we'll get? It is nothing but 4a square. So all bright fringes, they have same intensity, and what is that intensity? It is given by 4a square. Then next we'll try to see what is the condition for destructive interference. And here that point P on the screen, or this intensity, when it will be minimum, what is the minimum value taken by cos? So here we have to take our cos square del by 2 to be 0. So for maximum, we have taken this value to be 1. But for minimum, we'll take this value to be 0. And for which values of del, this cos square del by 2 will be 0? As you can see, it is 2n plus 1 pi. It means that what are those values we are taking? We are taking the values of pi, 3 pi, so odd multiples of pi, 3 pi, 5 pi and so on. Whereas for 2 pi, 4 pi, 6 pi, we got maximum intensity. And here when we are taking phase for destructive interference or minimum intensity, so odd multiple pi, 3 pi and 5 pi. And if I use this relation in order to find path difference, I'll end up having path difference as odd integral multiple of lambda by 2. So what are those values? You will have lambda by 2 and then 3 lambda by 2 and then 5 lambda by 2 and so on. So these are the values for path difference. And what is our intensity? Because of destructive interference, intensity will be 0. So one important thing we have to understand here is when we say minimum intensity in 0, we are talking about completely 0 or dark fringe. There won't be any intensity. So complete intensity will be 0. And when we talk about the bright fringe, its magnitude, it is given by 4a square. And what we have to understand here is all bright fringes, they'll have same intensity, which is given by 4a square. And if we try to plot this intensity or energy distribution with respect to phase, then we end up having this intensity distribution graph. So what we have done here, we have taken on x-axis phase value, and here we have taken phase in terms of pi. So we have taken phase to be 0, pi, 2 pi, 3 pi, and also we have taken other axis also where we are considering minus pi, minus 2 pi, minus 3 pi, and so on. And on y-axis we are trying to find what is the intensity on the screen. And here we have seen that what are those values of phi for which we'll get maximum intensity. Those values are 0, 2 pi, 4 pi, and 6 pi. So wherever I have those points 0, 2 pi, 4 pi, and so on, my intensity is maximum. And what is the value of maximum intensity? It is given as 4a square. So you'll have all bright fringes, they are of same intensity. And what is that intensity value? It is given by 4a square. And whereas coming to minimum intensity, where we have 0 intensity, what are those values of phase? Here it is given as pi, 3 pi, 5 pi, and so on. So wherever we have these points pi, 3 pi, and 5 pi, our intensity is 0. So this is very important intensity distribution curve as a result of interference. So interference, as you can see, it will give rise to bright fringes. So as you can see on the screen, because we made use of monochromatic source, so you'll have our bright fringe, white in color, then we have dark fringe where intensity is completely 0. And at those points where we have bright fringe, we'll be able to see those bright bands and then followed by dark bands. And one very important point, what we have to consider in the phenomena of interference is, interference, it is based on law of conservation of energy. And we know what is law of conservation of energy. According to law of conservation of energy, energy can neither be created nor destroyed. Now how it is applicable here? We are seeing that at dark points intensity is 0, and where that energy is going, actually it is getting transferred to bright points where intensity is 4a square. So here intensity of light, it is not getting destroyed, simply it is transferring from dark points to bright points. So this is very important point that we have to consider when we take this phenomenon of interference. So here today in this session, we have taken Young's double slit experiment. In that Young's double slit experiment, we try to get the conditions for bright fringe as well as dark fringe, and we try to get those conditions in terms of phase, also in terms of the path difference. So today we are going to end our session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.